Welcome to lesson 16 of our friendly introduction to abstract algebra. In today's rather short lesson, we are going to learn about a very fundamental theorem about subgroups, or the order of subgroups in finite groups. So-called, very hard for me to pronounce, Lagrange's theorem. Named after Joseph Louis Lagrange, Italian-French mathematician and physicist, absolute genius, became professor at Turin when he was only 19 years old. He did a lot of great things for math, physics, astronomy, and so on. And Napoleon once called him at the top of the pyramid of all the mathematical sciences. All right. So, as always, we have a group G, we have a subgroup H of this group G, and then we prove the following lemma, namely that all the H cosets are of the same order or have the same cardinality as sets. The proof is pretty simple. We take any arbitrary element in G, and then we take the left translation by this element, but not as a map from G to G, but as a map from H to the coset GH. And as the name suggests, it is simply multiplying any element of H from the left with the element G. This is clearly well defined because the codomain is defined as the coset GH. So clearly this lies here. And now this clearly is a bijective map. Why? Because its inverse is simply left translation with G inverse. Write that down if you don't believe it, but if you have done lesson 12 and the exercises, this should be clear to you. So now, clearly, the left coset GH is the image of LG, because by definition I end up with the left coset if I multiply all the elements of H from the left with G. So the order of the coset GH is nothing but the order of the image, but since this is a bijective map, this is the order of H. And for finite sets here, this is very obvious, and for infinite sets, we could have an infinite subgroup of an infinite group. By definition, if there exists a bijective map from one set to the other, then by definition they have the same cardinality. So in both cases, G finite or infinite, at the order of G finite or infinite, this is true. Okay, now we can already state and prove Lagrange's theorem. Now in this case, G must be a finite group. So I take a subgroup, any subgroup of a finite group G, then this theorem asserts that the order of H must be a divisor of the order of G. And the index, this is the number of different left cosets, as defined in the previous lesson. The index of H in G is nothing but this quotient here, the order of G divided by the order of H. And as we just stated here, this is a natural number because H divides G. Now about the index, I have seen both notations like so with these brackets or simply with these lines. Actually, in my little booklet I used this notation, but in the last video somehow I changed it to that, so I'm going to stick to that. So we will denote the index by these brackets here. Okay, let's prove this. The proof is deceptively simple, but you have to keep in mind that we did all the work before that we are going to use here. So, if I have a finite group, of course, the index of H in G must be a finite number, because it's the number of different left cosets of H, so this can't be an infinite number if G is a finite group. So we abbreviate this index here with the natural number n. And index being equal to n means exactly that there are n different left cosets which I denote like this, G1H, G2H, and so on up to GNH. And these different cosets form a partition of the group, meaning the group can be written as the disjoint union, that's this dot here, disjoint union of all these cosets. I is running from 1 to n. So, but that means that the order of G is simply the sum of the orders of all these cosets, where I again runs from 1 to n, because I have a disjoint union. Otherwise, this need not be true, but if I have a disjoint union, this is true. But in the lemma above, we just proved that this is always the order of H. So I sum n times the order of H, and then I'm already done, because then the order of G is nothing but n times the order of H. So the order of G divided by the order of H is a natural number, which means exactly this. And since n was the index, this result here follows. The index n is exactly this quotient here, which is a natural number. Now, this proof looks deceptively simple, and you could think, well, I could have come up with that. What's so great? Why does this deserve to be called Lagrange's theorem? But you must not forget that we used all the machinery that we developed so far, namely that a group is partitioned by the left cosets, because the left cosets are equivalence classes of a certain equivalence relation, and so on. So without all this machinery of modern abstract algebra, this result is not so obvious. And back in Lagrange's day, there wasn't yet a real developed apparatus of algebraic machinery. And now, why would this be important, this theorem? Well, it asserts that this here, the order of G, which is a mere number, contains information about the group structure or the possible subgroups there can be. And this is a very strong result. For example, take the integers modulo 42. Then, for example, the number 20 is not a divisor of the order of this group, 42. So Lagrange's theorem asserts, well, then there can't be a subgroup of order 20. Because if there were a subgroup of order 20, 20 must be, or would have to be, a divisor of 42, which it is not. If you try to find that out, for example, using group tables or any elementary arguments, this would be very hard. You can try if you want to prove that there is no subgroup of order 20. But with Lagrange's theorem, this follows immediately. Now, to conclude, the converse statement of Lagrange's theorem is not correct. What would that be? Here we have, if I have a subgroup, then its order divides the order of the group. So let's turn this around. If we have a divisor of the order of a group, then it is not true that there always has to be a subgroup with this order here. Easiest example is A4, the alternating group. We haven't talked about that in detail yet. It's a subgroup of S4 with 12 elements, and it can be shown pretty elementary that there is no subgroup of order 6 of this group here. The converse statement of Lagrange's theorem is not correct. All right, this is it for this week's lesson. Rather short, but a very important result. And as always, I would suggest you try to do some of the exercises on problem set 16. All right, thanks for watching. Hope to see you soon again. Bye-bye.